a brief introduction about myself. I am Daniel Chen. I work as the stream infrastructure engineer over at LinkedIn and have been primarily working on Beam integration with Samza Runner, specifically on the portability aspect. So this talk is mostly going to talk about how we are scaling these Python portable runtime pipelines and how we're increasing adoption for the Python pipelines nearline systems in LinkedIn. This talk is going to be separated into four major sections. Major sections of this talk is talking about the Apache Samza, as well as how we integrated Samza Portable Beam with the Samza existing nearline pipelines. This might serve as a review for some of you, but I think it is important background as we move through the new portable use cases that we have developed over time. And this is very important for us to get that important background to look at how we scaled some of these issues that we have initially encountered in the portable integration. Finally, I'm going to finish off with some future work we have in this area. There is a lot of work left, and I just want to break it down into what kind of areas we want to focus on going forward. So let's start off with Apache Samza. I really want to iterate why we're using the system on LinkedIn, how it scales, at what scale we're using this, what are the typical use cases that exist today, to give you guys some background on why potentially portable comes into play. So a little bit of a history. First, Samza is a distributed stream processing framework. It is built to handle stateful applications to process data at scale. So this distributed frame processing framework has been developed at LinkedIn in 2013, and it has been a top-level Apache project with 13 major releases, the last one being earlier this month in August. It's been used by many companies in the industry, primarily at LinkedIn, and a slew of other companies as well that we form a nice open source community with. So to give over a very basic high-level overview, Samza has, at its core, is a stream processing framework. It is horizontally scalable, so a Samza job contain one or multiple containers, and these containers could have one or multiple tasks that processes exactly one partition per task. So this is a very nice property of Samza, is that it's stateful processing. For each task, we have a respective state. The state is very important for us for many of our use cases. And it is durable, it is backed up, and I'm going to cover a little bit over the next slide as to how exactly we're achieving this. Also important to note is this job coordinator section could be swapped out. We have Yarn job coordinator, which is used for the majority of our use cases at LinkedIn. It's a great resource negotiator. And we also have Samza as a library, for which case this job coordinator would be backed by Zookeeper, similar to Kafka. Of course, the other interchangeable part is this input stream. So for the majority of the use cases, this will be Kafka, but it could be any different IOs. And I will cover the overview of the LinkedIn ecosystem in a little bit. So moving on. So Samza, again, I would really want to reiterate this, it's really built for scale. This incremental checkpointing with the state change log is a part that I mentioned in the previous slide, where we have a local state. This state is backed up by incremental checkpointing right through to a Kafka topic, which we call the changelog. And upon a machine failure or job restart, this is reloaded back into state. Now, this might work for smaller jobs. The Kafka reread time is relatively fast. But when we reach at a larger scale, we need other tools to deal with this. Because in Samza, we actually have containers or customers that are using state that is up to 1 terabyte. And for that, it takes a lot more time to restore that state. So we have these two next features are mainly used to address this. Host affinity is the feature that every time we come back, every time the state comes back, we try to match it to a previous host that it is failed on. Or upon restart, we match the container to a specific host that it was on in order to retain that state. The state, by the way, is implemented by rocksdb. So upon restart, the new container will be able to find the previous rocksdb state, and therefore costing virtually no time for that restore. Further, we have standby containers. If for some reason the host that your job failed on was actually bad, we have these shadow containers running in the background on separate hosts that actually has the state that you would have in your failed job. So that way, during restores, we try to match these containers to these standby containers in order to restore state. And a relatively new feature we have is autoscaling. Autoscaling is very useful for use cases where our job is processing a huge amount of data that is very spiky sometimes, and we do not want to waste any resources during the downtimes. So this is a very interesting new feature that probably deserves a talk by itself, but it is very important to how we deal with the scaling at LinkedIn. So by the numbers, we have today at LinkedIn over 2 trillion messages processed per day, and this could come from a variety of input sources, writing to a variety of sync destinations. These include mainly Kafka, Brooklyn. We also have support for Kinesis and Event Hubs. We have over 3,000 jobs in production and with a variety of use cases. I think one of the interesting parts about LinkedIn is that in terms of use cases, because a lot of our data is actually in Kafka, we are more expressive in terms of the time pipelines we compose, and stream processing becomes very important for us. So we have notifications, fraud detection, data standardization, feature scoring for ML, and much more. This is run over 3,000 machines. As I mentioned earlier, it could be either run on Yarn or as a library that is more lightweight. I'll cover the deployment models later because that is actually also relevant to portable pipelines. And of course, we have 4.9's availability here. No surprise, and this is for our Yarn clusters. In order to keep our customers' confidence, in order to run a business as an infra team, this is very important to us, and it is top priority. A brief overview of the ecosystem. It's not only Samza that is very fleshed out, the variety of use cases, but it's really the ecosystem around it, the number of systems that we actually interact with that allows us to see this behavior as a way of interacting with a lot more different systems. So this forces us to come up with different use cases, or this allows us to come up with different use cases using a different combination of interacting with different systems. So mainly, as I mentioned, is with Kafka. I mentioned that Samza is somewhere about over 2 trillion messages processed, while Kafka probably handles over 5 trillion messages daily. Um, and Samza reads and write from the system, as well as Brooklyn, our change capture system that has been open source relatively recently within the last year. It's a very cool project. Check it out. That listens to the changes on our DBs. And of course, we can read and write from a variety of our different tables. We have Venice, our distributed key value store, Pinot, our OLAP store, which has also been open source within the last year, Couchbase for caching, and even offload to HDFS for ETL and offline training workloads. And all this interacts with our app services to deliver the best experience to our users. So now that I've given you a feel of the Samza, how Samza is used as at LinkedIn, we can really say this is processing at a truly large scale. It is very scalable with features like hostability, with features like standby containers, and it is fault tolerance and fast recovery with high availability. So this is a very go-to, battle-tested the engine that we use in production. Together with Beam, on the other hand, we have a very state-of-the-art API for processing and a great model that is very easy to understand. At the same time, the main bulk of this talk is going to be about this portability framework feature that is very, very impressive and I believe very crucial to operations at LinkedIn as well. For LinkedIn, we actually have the second most used language apart from Java. It is actually Python. So this is a really great motivation for us to invest in this. Furthermore, we have a great ML pipelines that are looking into new ways to train their models. And this is a great time for us to offer this portability option, this Python option to our users. And not to mention, Beam has great SQL and DSL support which we are also, as a Samza runner, looking into investing into. So let's dig deeper into this portability framework and how we're using the Samza portable runner. So this is probably very familiar for you guys at the Beam Summit. We have a Java SDK or Python SDK, Go SDK in the future that is translated into a language-independent protobuf pipeline. And it is eventually sent over to the Samza runner in order to execute. What is really cool about this is how we do the translation. If we zoom in on that, it turns out regardless of portable runner, regardless of Java runner, it's very important that we have these 4 core transforms to be transformed, four transforms to be translated rather into a Samza pipeline. So for I/O, we have a very equivalent system, a very equivalent concept in Samza, which is the system consumers and system producers. As I mentioned in the ecosystem slide, we are consuming from a large variety of different topics and can produce to a large variety. So this is pretty much covered. We do need, however, here to generate the watermarks as well, because Samza natively doesn't support event time. The next part is Pardue, and this is where it kind of diverges between the portable runner versus the actual Java runner. We have simple do function runner for the Java pipelines and executable stage do function runner. This executable stage do function runner is, as its name suggests, executes the stage and passes the processing of the UDFs to the pipelines in Python via the SDK harness. So this continues to inject the Samza watermarks, state, and timers. Window is relatively straightforward. We just invoke the window assignment function. And for the group by key here, we have a variety of merging transforms in Samza as well that we invoke here in order to overall generate the Samza DAG, which is submitted to the Samza job runner and is passed on to the Samza cluster where it is executed in our containers and tasks. So before we dive into the how the portable runner works, we would like you to take a look at how it looks like in code from a user's perspective, because part of the importance of scaling these pipelines is essentially have users that want to use it, and for that we really need a nice API. So for the transforms that I mentioned earlier, the read from Kafka would be transformed into a Kafka system consumer for the Samza side. And an important thing to note here is that for Kafka, we actually, all the I/O comes through Java and is passed to the Python process. I'll talk a little bit more about that a little bit later. The next part is the transforms, the Lambda, the process event. This is the executable stage, which gets passed to the SDK runner to be run as a UDF here. And everything else gets transformed, as I mentioned in the previous slide, except for Pardue as well. This is passed back into the Python process. And right from Kafka, similarly, we pass it to Java and it gets written to the specific cluster and the specific topic. We have a large number of clusters, so the normal API for defining which Kafka cluster to write to and which Kafka clusters to read from is baked as a argument to be passed in here. So portability is really, as my co-author coined it, a tale of two languages. At the end of the day, we have two processes here, the Python and Java process, and it's all about the communication between these two processes. The Beam pipeline is submitted through, just to give an overview, I'm sure this is not news for most of you. The Beam pipeline is submitted through gRPC to the job server, which is then translated to the Samza task. I covered this a couple of slides ago. And each these Samza tasks execute the most of the work. It is really when we reaches the UDFs that we want to pass the data back to the SDK workers during those executable stage moments. Everything else, I/O, stage, shuffle, join, everything we want to handle on the Samza task. And that really helps us develop more more features on the Python side and not focusing on rewriting some of the existing work. And by the way, cross-language pipelines would help us with that. This is probably a future work item that we will look into more. So as I mentioned, it is really about the communication of these two processes. At first, we have every message we send it back and forth to Java and Python via the data channel. And this is pretty bad in terms of QPS. We had 85 QPS per container. Really drags down the performance. So we decided to add this, reduce the network delay, reduce the increase the amount of data transferred per round trip. We decided to put this into a small bundle or micro batch, if you will. So how that works is every time we send it over from Java to Python, we would have a buffer. This buffer would hold up to n messages, and will fire after t seconds. So it would fire after the max of n messages or t seconds. And really, this buffer needs to be backed up, because upon job restart, we need to restore the state, which is why uh, the rocksdb state comes in. So we use rocksdb in the background in order to store all this buffering. At the same time, this is also in a similar way backed up through the Kafka changelog, similar to the Samza state. So this is very nice, and it improved our processing speed significantly, which allowed us to handle much more scale. So this is some data points that we have. At one bundle size, we can see that it is pretty terrible per container QPS at 85. As we increase this, the QPS increased greatly. At one point, it kind of dips off. That's because of the delay of processing that usually occurs because we're holding in the bundle the messages that could have processed if we had shipped it off already, which is why we set a time for the bundle as well as the size as a firing condition. To briefly go over the current deployment models we have for Python, the one that is currently used is standalone mode. As I mentioned, this is coordinated by Zookeeper. Every task would have a Python process and a Java process. The Python process creating the job, and those two communicating during execution time. This Python process is actually doing all the work to manage life cycles, and this inter-process communication becomes very important. The coordination is always done via Zookeeper here, which is out of the box available from the Samza engine. And another deployment model we have been experimenting with some success is using interactive Beam. This work is actually in very early phase. The main motivation is so that when people have a less overhead on working on nearline processing pipelines, really allow people to visualize what's going on and allow them to try out different things in an environment that maybe data scientists and machine learning engineers are more comfortable with. So we have adopted this to use the Samza engine as well. This serves as a front end, as an alternative front end right now. But the next step we need to do internally is to productionize this and work with the existing team at LinkedIn to merge this with our existing Jupyter Notebook hosted offering. And the other work in development is standalone cluster management mode. So Yarn, as I mentioned, is the majority of use cases for Samza today. We have most of our jobs running in Yarn. Most of our customers who don't want to deal with any of the specific host management duties. We have an SRE team that monitors this Yarn cluster, making sure that it has 4 nines availability. This obviously comes along with the nice properties like isolation, multi-tenancy, and fault tolerance as well. This is something that we're looking into to work on more in the future. So with that, we have covered basically an overview of what we've done from the Samza side to really support the portable framework in LinkedIn. It's very interesting that a lot of the work that have been done in the past year has been onboarding new use cases at LinkedIn. So we've done a lot of the work as described in the previous few slides in the past. So some of you may have seen this already, but it's really the new use cases that we have been working on in the past year. And I have shared a few that I found that are very interesting. The first one, this has been in production for a while. We have a image data in Kafka, which is an image URL, and this actual portable job is reading the REST service, and you really use the TensorFlow model for OCR. What this really illustrates is that the first use case at LinkedIn for these portable frameworks, the first type of use case is really to, with good ML integration, break that barrier of mostly using offline for these OCR kind of learning workflows. So what this does is it retrieves a message URL, requests the actual image from a REST service, and loads the OCR TensorFlow model into memory in order to parse the image URL, the text from the image URL, send this result to Kafka to be processed. And it's a very simple use case, but it really illustrates the new type of customers that we will now able to be onboarding at LinkedIn to use a portable pipeline. The next one is probably the most common type of use cases. We have a normal processing of a Kafka stream and emitting this into some other topic, no fancy machine learning. This really highlights how simple it is to construct a pipeline in which the user could have a limited understanding of stream processing, and they are now more inclined to adopt this kind of workflow. And how this works is especially to detect abnormal activities. When an abnormal activity occurs inside a specific host for a specific IP, this gets extracted and combined into a fixed window. And if that threshold exceeds some set amount, this triggers an alerting system. Very similar, very relatively simple, nice use case that is now done in the Java, the portable pipeline. It could be done in Java pipeline, but some of the Python users at LinkedIn would prefer this method. And I'm glad we're offering a platform for them to do that. The next model is using some kind of random forest inference. So this is very similar to the previous use case. This is a group of SREs at LinkedIn working with the ML team, both groups of which are heavily users of Python. So it's really nice to join those two groups together, forming these type of use cases. So what this does is preemptively identify hosts that could potentially fail. So what they do is they get a host logs from Kafka, and these are all the events that the host undergoes. They rekey it per host inside a sliding window, I believe, for 30 minutes, large enough to actually form a prediction from the model store. Again, this here is using a model to predict based on the last X minutes of host log data whether this host might potentially fail. They managed to predict this relatively well and send this to a monitoring system. Because of this setup, we have a preemptive approach to failing host rather than purely reactive. And the next one I want to cover is a Fanout service. This is very interesting because it is an evolving pipeline. So every restart, what this pipeline does is it pulls from this online REST service, the filter requirement updater service. So this pull is done outside of the pipeline in the main function. And every time this filter requirements gets updated, they could actually change the pipeline on the fly. And this pulls happens every set amount of time. And every set amount of time, this pipeline would evolve. So why are they doing this? They're actually doing this because they want to really have a categorized way of accessing only the events that a specific team wants. So for example, this is reading from unsorted events. This has all the tooling and all the events in LinkedIn that revolve around, for example, builds and pull requests and etc. For example, one team will want to access only the pull requests, and this filter is updated. They enter their requirements into the filter requirement updater service. After X amount of time, this filter requirement gets updated. They add their destination. The filter is updated and the destination is updated. When both of those are updated, this job can filter the events and send them to the destination that they want. Of course, the purpose of having this is so that you wouldn't filter two topics similarly. So the online service will take care of that, which is a very interesting use case, very interesting fan-out method that is used to categorize a unsorted Kafka event queue. And this nearline model training is probably our largest job and the customer that is really pushing the envelopes when it comes to the support we have on portability at LinkedIn. So first of all, their QPS peak is 10K, which was unachievable previously with our low QPS without bundling. So we helped them fix that. And they're reading sequentially from a coefficient store to as well as processing, as well as writing to that coefficient store, which we have not had before. They have requested that feature as well. Essentially, it's making a table join in this case in their nearline system. So to give you a brief summary, I'm not an ML engineer here, but how it works is they have a offline training and a online training component. The offline training component is updated much less frequently. It is not always the latest information. So they have adopted this more Lambda-like feature model. So we have on one hand the fixed windows with the trigger and a group by key. The fixed windows again is to gather enough data in order to do some training on. and they're using sequential Bayesian updates here in order for the model training to be very quick. The sequential model updates and the offline training all access the same coefficient store. So in order to keep that coefficient store more up to date, this nearline model comes in and updates it as training events occur, instead of once every day or so. So with this hybrid approach, we're actually seeing a higher convergence on these models. So the purpose why they're having this kind of two approaches is that they want to calculate data such as click-through rate for ads. So with this addition of this nearline component, they're seeing a increase in the more recent ads convergence. So actually, this team is planning to have a paper out about this specific training model later this year, and stay tuned for that. So this is one of the key partners we have at LinkedIn in order for adoption of the ML team. So we're really waiting on this, who are really waiting on this to come to fruition before thinking about adopting nearline processing for training models. And this will be a huge step for us. In summary, these are a lot of the use cases that are available on LinkedIn. In the past year, we really focused on gaining more customers. We have great work done in the portable runner area for Samza, and we're really trying to adopt more users in the past year and helping them, guide them through this new nearline processing world. And in the future work, we have a lot of things planned for the portable area. So cluster-based deployment for Python is actually a must. For pipelines with Java, we offer a very nice suite of features that come with Yarn. Because if it's deployed on Yarn, we actually own those machines. We write a bunch of tools around this, such as dashboard, nicer alerting, and of course SRE support for those specific hosts. Cross-language support pipelines is something that I'm very excited about. I believe the community is as well. This is going to significantly help us in terms of reaching feature parity with the Java offering without every time the Java develops something, we need to write any duplicate. We can invoke the Java call directly. iBeam is work that we have already started. People have seen interest in this. We need to, on our side, productionize this feature and prioritize this work. Portability tests and more features are very important. So portability is test essentially allows us to release more quickly with confidence. The portability test in open source is actually very required here. By portability tests is we need to add the open source test integrated into our existing tests in order to have more confidence. We should also have more frequency of merging from the open source branch to keep up to date with these things. More features as we have more customers, like the nearline machine learning model. As we have more features, this will grow naturally. We are hoping to tackle these new features as well. Again, this is based on a use case basis. Of course, to achieve feature parity, these are all necessary work that we need to think about. And finally, Golang. We already have a prototype for this. It is currently more of a hackathon project. that my coworker have worked on the side about this, and we do have some use cases at LinkedIn that is using Go and would be interested in this as well. Um, yeah, in general, there's a lot of work to do. Currently, I am the only one working on the portability section here. So there is a lot of area to grow if we want to really scale this. But this past year has we've seen great success in the increasing adoption. I think the adoption almost doubled with more jobs coming down the pipeline. I see that this is accelerating in terms of growth inside LinkedIn, and I'm excited to be a part of it. With that, I want to thank you all for listening to my talk, and I would like to open some time to questions.
Thank you very much, Daniel. Good to see that both Beam and Samza are getting a lot of traction at LinkedIn. And also good to see there's a lot more to come. Thanks for sharing that.